Okay, let's get into it. Today, we're doing a deep dive into something called the Amplituhedron. It's been described as this jewel at the heart of quantum physics.
That's a pretty evocative description.
It is, isn't it? Apparently, it massively simplifies how we calculate particle interactions.
Yeah.
So our mission today is to understand, well, why? Why is this shape so much better?
It's a really fascinating shift in perspective. So the concept itself was introduced, about a decade ago, 2013, by Nima, Arkani-Hamed, and Jaroslav Trnka.
Right.
And it's important to remember, while the potential is huge, it was first developed for a very specific sort of mathematical toy model.
Okay. Not quite the real world yet.
Exactly. It's called planar N4 supersymmetric Yang-Mills theory. Highly symmetric, very idealized. It's basically the simplest arena where these geometric ideas, well, they just work perfectly.
That context is definitely key. So let's break it down for everyone listening. What is this amplituhedron? I mean, fundamentally, it sounds incredibly complex.
Well, yes and no. At its core, it's geometry. Think of a simple shape like a pyramid or a cube in 3D. The amplituhedron is like that, but higher dimensional. It's what mathematicians call a polytope. It's a geometric object.
A higher dimensional shape.
Yeah.
And how does that relate to particles smashing together?
Right. So when particles interact, physicists calculate something called a scattering amplitude. It basically gives you the probability of a certain outcome happening. What's amazing here is that this amplitude, this probability, corresponds directly to the volume of this amplituhedron polytope.
So instead of endless equations, you measure a volume.
Essentially, yes. You calculate the volume of this specific shape in a particular mathematical space.
So we're ditching the old way, the sort of probability tree of possibilities. Why go for geometry? And why this abstract space you mentioned?
Well, the standard methods get complicated very quickly. This geometric approach provides a massive shortcut, but you have to step outside of our normal space-time view.
Outside space-time.
Yes, the calculation itself, the geometry, lives in what's called momentum-twistor space. It's an abstract mathematical construct where the physics simplifies beautifully. And specifically, we use the positive part of that space. That positivity defines the amplituhedron's facets.
So the shape isn't in our universe, but it describes it.
Precisely. The geometry exists there, but its volume gives us the real-world scattering probability.
Okay, this feels like where the big simplification comes in.
Yeah.
The traditional way involves Feynman diagrams, right? Can you paint a picture of what we're avoiding?
Oh, absolutely. For anything beyond the simplest interactions, using Feynman diagrams means calculating, sometimes literally, thousands of individual diagrams.
Thousands, wow.
Yes, and each diagram represents a possible path the interaction could take, including paths with these virtual particles.
Virtual particles, the ones that pop in and out of existence for tiny fractions of a second, the ones we can't actually detect.
Exactly those. They're mathematical tools needed in the Feynman approach to make sure everything adds up correctly, like conserving energy and momentum at every step. They're considered off-shell, not quite real in the same way.
But the amplituhedron calculation, it just skips them.
It completely bypasses them. It gives you the final answer, the total amplitude, directly from the geometry without ever needing to sum up contributions from virtual particles.
That's huge.
It leads to radically simpler mathematical expressions for the same physical outcome. And it really makes you wonder, if the geometry works without them, do these virtual particles even need to exist, even mathematically?
So this geometry might be more fundamental than our usual picture of things happening step by step in space and time.
That's the really deep implication here. The amplituhedron suggests that maybe, just maybe, concepts we think are absolutely fundamental aren't the starting point.
Like what?
Like space-time locality and unitarity. Locality is the idea that things can only directly affect their immediate surroundings, constrained by the speed of light.
Right, cause and effect.
And unitarity is basically the rule that probabilities must add up to 100%. Something must happen.
We always assume those are built into the universe, the basic rules.
We do. They're usually inputs into our theories. But in the amplituhedron picture, they're not assumptions. They actually emerge as consequences of the geometry itself.
They're outputs, not inputs.
Exactly. Locality and unitarity seem to arise naturally from the mathematical properties of the geometric volume, from this geometric positivity we mentioned. The shape itself guarantees these physical principles hold.
That turns physics inside out a bit. No wonder Edward Witten called it very unexpected. The universe's rules emerging from a shape.
It's a profound shift. So the key takeaway really is this. We've potentially traded thousands of complex diagrams full of virtual particles for calculating one geometric volume in an abstract space.
And in doing so, found that core principles like locality and unitarity might just be features of that geometry, not separate laws we impose.
Precisely, they come out naturally.
Which leads us to that final thought for you to ponder. If core ideas like locality and unitarity are just shadows cast by some underlying geometry, what other bedrock principles of physics might also be, well, geometric illusions, just waiting for us to discover the right shape?